In this lecture we will introduce the language of propositional logic. We shall first discuss what is a proposition, then we shall give a precise definition of the syntax of a language of abstract propositions and explain how to use this definition to build abstract propositions. And finally, we shall give some precedence rules that allow us to economize on parentheses when writing abstract propositions. A proposition is a statement that is true or false. An example of a proposition is, for instance, the statement, "the grass is green." This is a true proposition, or at least it was true when I took this picture of the campus of Eindhoven University of Technology. You may notice that there are some trees in this picture that have red leaves. So all trees are green is a proposition, but it's false in the context of this picture. And the grass is green and not all trees are green would again be a true proposition in the context of this picture. A proposition need not be a sentence in natural language. It may also involve mathematical expressions, again provided that it evaluates to a truth value. For instance, 3 plus 5 is less than 10 is a true proposition formulated in mathematical language. 10 is less than 3 plus 5 is also a proposition, but of course this one is false. An example of a proposition that mixes natural and mathematical language is, if x is even, then x squared is even. This proposition is true, and in fact we shall discuss a proof of this proposition in a later lecture. And for our last example, the statement, "every even integer greater than 2 can be expressed as the sum of two prime numbers," is also a proposition. Interestingly, although we do know that it evaluates to either true or false, and therefore can say that it is a proposition, we do not know which truth value we should assign to it. We do not have a mathematical proof, nor an example of an even natural number greater than 2 that cannot be expressed as the sum of two prime numbers. The statement is a famous open problem of mathematics, known as Goldbach's conjecture. Propositional logic aims to study reasoning about propositions in as general a setting as possible. It is therefore convenient to be able to abstract from the actual contents of the propositions and focus on their logical structure. For instance, in a proposition like "the grass is green" and "not all trees are green," we would like to abstract from grass and trees and their colors, and we would like to focus on the logical structure. We would like to focus on the fact that it is built from simple propositions, "the grass is green" and all trees are green, by means of constructions like "and" "not." Let's now introduce a language of abstract propositions. First, we fix the vocabulary of our language. To represent simple propositions, we shall use proposition variables, generally denoted by lowercase letters from the beginning of the alphabet. Then, our vocabulary also introduces special symbols called connectives that we shall use to compose more complex abstract propositions from the simple ones. The language of propositional logic includes 5 such symbols: a wedge-shaped symbol to denote conjunction, and a V-shaped symbol to denote disjunction, or a special symbol to denote negation, not, a double arrow from left to right to denote implication, if then, and a two-headed double arrow to denote by implication, if and only if. Let's return to our example proposition, letting the proposition variable A stand for "the grass is green" and the proposition variable B stand for "all trees are green." We can now write this proposition in our new language by means of the formula you see over here. The formula is called an abstract proposition. We now have a vocabulary for our language of abstract propositions. We proceed to add a grammar, and together vocabulary and grammar are called the syntax of our new language. The syntax of abstract propositional logic tells us exactly how to build abstract propositions. The first clause states that every proposition variable is an abstract proposition. The other clauses will explain how the connectives can be used to build complex propositions from simpler ones. If P is an abstract proposition, then we can make another one by writing a negation symbol in front and enclosing the result in parentheses. If P and Q are abstract propositions, then we can make another one by writing a conjunction symbol in between and enclosing the result in parentheses. or we can write a disjunction symbol in between and enclose the result in parentheses, or use an implication symbol, or a by implication symbol. The specification of the syntax is an example of a so-called inductive definition. Towards the end of this course, when we discuss the topic of induction, we shall explain more precisely what that is. It is important to note that a string of symbols from the vocabulary of our language is an abstract proposition only if it can be built in accordance with these clauses. Let's illustrate the use of the definition of the syntax of propositional logic with a few examples. By clause 1.1 of the definition, which states that every proposition variable is an abstract proposition, we may conclude that the proposition variable A is an abstract proposition, and also that the proposition variable B is an abstract proposition. Continuing with the abstract proposition B, since it is an abstract proposition, by clause 2.1 we may conclude that if we put a negation symbol in front and enclose the result in parentheses, we get a new abstract proposition. Then we may combine the two abstract propositions we have now, A and not B, by putting in a conjunction symbol in between and enclosing the result in parentheses. This gives us the new abstract proposition A and not B. We continue with an application of clause 1.1 to conclude that the proposition variable B is an abstract proposition, and then we can combine the two abstract propositions we have, A and not B and B, by putting an implication symbol in between and enclosing the result in parentheses. This is an application of clause 2.4. The structure you see over here is called a proof tree, and it can be considered as a concise notation of a proof that the formula at the bottom, at the root of the tree, is an abstract proposition. Now consider another proof tree, and let's check that this is indeed a decent argument that A and not B implies B is an abstract proposition. Indeed, A and B are abstract propositions by clause 1.1. Since B and B are abstract propositions by clause 2.4, so is B implies B. Since B implies B is an abstract proposition by clause 2.1, so is not B implies B. And finally, since A and not B implies B are abstract propositions, so is A and not B implies B. It may have occurred to you that we write a lot of parentheses when writing abstract propositions. And this is actually necessary to be able to reconstruct how the abstract proposition has been built in accordance with the syntax. Note that if we omit the parentheses from the two abstract propositions at the bottoms of these two proof trees you see over here, then they will become identical, whereas the proof trees look different. And this is bad because it matters whether we consider an implication of A and not B and B, or a conjunction of A and not B implies B. Later, we shall see that these two abstract propositions have different interpretations. So we would like to omit parentheses, but not too many. We would like to be able to reconstruct how an abstract proposition has been built according to the syntax. Let's consider the three abstract propositions you see here and determine which parentheses can be omitted without introducing ambiguity. Clearly, the outermost parentheses of an abstract proposition can always be omitted without introducing ambiguity. Also, when we omit the parentheses around the negations in the first and second abstract propositions, we will not introduce any ambiguity. Note that omitting the parentheses around the negation in the third abstract proposition appears to be risky. It may no longer be clear that the negation is applied only to B and not to B implies B. Instead of by using parentheses, we could, however, also resolve this ambiguity by saying that negation has a higher precedence than implication. It is convenient to do so, and we shall assume, more generally, precedence of negation over conjunction and disjunction, which in turn have precedence over implication, which has precedence over by implication. In accordance with the precedence scheme, we can now also omit the parentheses around the negation in the third abstract proposition. And since conjunction has precedence over implication, we can also omit the parentheses around the conjunction in the first abstract proposition. Note that conjunction and disjunction are not ordered according to our precedence scheme. So we cannot omit parentheses from A and B or C, nor from A and B or C. And in fact, we shall see later that these two abstract propositions have different meanings. This concludes the introduction of the syntax of the language of propositional logic. In the next lecture, we shall discuss the semantics, the interpretation of the constructions of propositional logic.